and today I will represent the Chong Zhang. He is currently an assistant professor at the Southwest Petroleum University at Chengdu, and the paper title is Legal Plus Redefining the Redundancy Removal for the IoT Sensing Agent System. The main function of the IoT end devices is to sense the world and provide rich data support for diverse applications like the smart building and smart agriculture, intelligent manufacturing, and fire monitoring. As of the 2023, the global number of IoT connections reached approximately 18 billion, and this figure is projected to grow to more than 40 billion by 2034. And to reduce the cost for the large-scale deployments, IoT sensor nodes should be designed to be as lightweight as possible, with minimum architecture, general purpose adoption, and also to be efficient in the sensing task. However, achieving this vision remains challenging today. The root cause is that currently, even the lightweight sensor nodes designed for the simple task, for example, the temperature sensing, are in essence based on the same general purpose embedded computer architecture as other high-cost IoT devices. Such an architecture can be programmed for different sensing functionalities, but on the other hand, it is practically inefficient due to the nonlinear relationship between energy consumption and workload. For example, if only deploying a little and easy, simple sensing task, we also need to apply the microcontrollers, the same architecture with a high energy and inefficient cost. So, however, the complex task is also accompanied by the high deployment cost and limits the large-scale applications. And for the lightweight design, one category of the existing work attempts to reduce the power consumption by decreasing the operating frequency, clock frequency of the microprocessors. However, such a solution does not help to reduce the task overload because it consumes more energy due to the prolonged execution time as the microprocessors have a poor energy efficiency at lower clock frequencies. And another category of existing solutions attempts to transfer sensor control to the gateway, thereby eliminating the need for the local microprocessors so as to simplify the node architecture and to reduce the cost and the power consumption. However, this kind of work essentially still rely on the gateway side remote microprocessor to control the on-node sensors. Consequently, a large amount of the raw information and massive underlying signals that were originally exchanged between the processor and the sensor chip are transferred to the air interface, resulting in a surge in the communication overhead. And so they are confined to backscatter communication for low power considerations. And meanwhile, such a solution is also limited in the versatility, as it is controlled sensors must be compatible with the specialized communication mechanism. And we observe that the tasks of the lightweight IoT nodes consist of 3 steps: data acquisition, data processing, and data transmission. And meanwhile, this process by which the node controls the sensing chip to acquire data and the subsequent data processing can be further broken down into the orchestrated combination of a series of basic atomic options. And based on this observation, our basic idea is to generate the required control logic through combination of hardware-level atomic operations, without relying on either the local microcontrollers or the remote microprocessors on the gateway. And this approach aims to simplify the sensing control architecture and improve the task efficiency, thereby reducing the cost and the power consumption for the large-scale deployment of IoT applications. And more specifically, we redesigned the sensing architecture and simplify the sensor node to transform into a highly complex, independent, embedded computing system into a simple, smart wireless peripheral of the gateway instead of relying on the general purpose processors. And so in this paper, we propose the Lego Plus. Our system generates the target logic by orchestrating a few atomic operations at the minimum hardware level on the sensor node. And we use the simple commands from the gateway, just like we construct the Lego bricks. And by doing so, our design not only simplifies the architecture, but also streamlines the deployment process of the large-scale lightweight applications. However, to achieve this architecture, we need to address two technical challenges. First, as a different sensor task involves the control of different sensing chips, and their upper layer data processing requirements and associated logical operations also vary significantly. It is hard to generate the required control logic using a simple circuit architecture without relying on the general purpose microprocessor. And second, for the large-scale deployment, several signal collisions may occur when multiple sensor nodes upload their data concurrently. But it is non-trivial to efficiently handle the coordination of multiple sensor nodes and to avoid the data collision at the micro hardware level with a simple architecture. To address the first challenge, we first designed a novel hierarchical task description language to uniformly describe diverse heterogeneous sensing tasks. Specifically, based on our observations, the sensing tasks, we decompose them into two hierarchical levels: the chipset layer, which is responsible for controlling the sensing chips, and the app layer, which manages upper level applications, like the processing of the raw data. And meanwhile, each subtask within each layer, control a specific sensing chip, can also be regarded as a sequence of basic state transitions. And the operations that controls a single state transition is an atomic operation. By doing so, we summarize the required atomic operations into concise keywords and design the new language. We call it a Hierarchical Task Description Language, HTDL. With this new language, the users can construct control profiles for diverse sensing tasks through the orchestration of a atomic operation, as simple as building the Lego blocks. Subsequently, to generate the executable binary control flow that can drive the micro hardware circuits on a node to form the required atomic operation orchestration for the task logic of the target application, we design a lightweight edge-to-end compilation logic. Specifically, we utilize the edge gateway to parse the task description profile. And with this profile, each atomic operation is mapped to a corresponding node based on its keywords and the variables. Subsequently, the gateway can operate these instructions to form a binary stream that describes the operation orchestration within the target task. And to implement the sensing and control logic required for the target application with a small microcircuit without relying on a general purpose computer architecture, we design a novel hierarchical atomic control circuit. on the node side. Overall, the circuit comprises 3 modules: an instruction dispatch module, a task logic storage unit, and a dual-layer sensing control module. So the first instruction dispatch module identifies and splits the atomic operations with the binary control stream using simple shift register and the simple gate circuits. It then routes these operations to the corresponding storage units in the task logic memory module. And the task logic memory module comprises dual-layer storage units dedicated to the sensing chip control and higher-level task logic with the storage of the binary atomic operations to predefined sequencing conventions. When the task execution is required, the operations are dispatched to the dual-layer sensing and control module in the predefined sequence order to execute the atomic operations, thereby generating control logic necessary for the target task. And finally, the dual-layer sensing and control module incorporates the micro-logic subcircuits for sensing chip control and higher-level data processing at the gateway. And subsequently, to coordinate the multiple nodes at the micro hardware level to prevent the data collision, we design a novel task status prediction and coordination mechanism. Specifically, although LEGO Plus simplifies architecture through lightweight hardware design, it sacrifices the ability to adjust the task and avoid collisions. Unlike traditional solutions that rely on running embedded programs based on the independent microcomputer architecture, meanwhile, in a practical application, each node operates independently. Therefore, collisions may occur when multiple nodes upload the data simultaneously and to address this issue, we designed a task status prediction and coordination mechanism. It calculates the relative delay in the data uploads for each node based on their task scheduling logic. And based on this calculation, the gateway can proactively adjust the task start slots for each node to avoid conflicts. And in practical applications, the gateway may utilize multiple communication channels with different signal frequencies that do not interfere with each other. And then this model can operate in parallel to support the coordination of a greater number of LEGO Plus nodes without relying on a general purpose microprocessor. And next, we design a lightweight protocol to control the operations of the microcircuits on the LEGO Plus node. In general, this protocol framework includes functions like the task configuration adjustment and task start and stop control and task status word detection. Upon receiving the command, LEGO Plus nodes autonomously invoke their hierarchical storage framework to execute the orchestrated atomic operations corresponding to the sensing tasks. And for example, in a motion detection application, we can configure the LEGO Plus node to read an accelerometer at a frequency of 200 Hz and determine whether the data exceeds a threshold or without relying on a traditional microprocessor. And meanwhile, this configuration process is only initiated when there is a need to modify the task node of LEGO Plus node. And it does not incur additional communication overhead compared to traditional processor-based nodes. In the prototype, we implement our LEGO Plus node using a low-power FPGA to control various onboard chips for proof of concept purpose. The architecture of the control circuits on the LEGO Plus node is designed to be ultra-lightweight, with its logic part utilizing only 2.6 kilo logic gates to generate the atomic operation orchestration required for accessing the internal states machine logic of the target sensor chips with standard digital interfaces, such as the I2C, SPI, and USART. And besides, users can also connect customized passive radios or commercial off-the-shelf active radios such as Wi-Fi, Bluetooth, and LoRa to the circuits using a UART, SPI, or GPL interfaces. Additionally, we provide a voltage adapter to accommodate the output voltage of some analog sensors, as their output voltage standards may not match those of our motherboard. And we conduct the experiments in various scenarios, including the indoor and outdoor conditions, and found that in terms of the communication overhead, although the communication cost of LEGO Plus nodes is slightly higher than traditional solutions based on the local microprocessors, it is significantly lower than that of existing processor-free nodes. In terms of computation, specifically the control of sensor chips, the power consumption of LEGO Plus is substantially lower than that of traditional local processor-based architecture, while being slightly higher than the existing processor-free nodes. This is because at the architecture level, LEGO Plus is significantly simplified compared to traditional local processor-based architecture. And besides, at the communication level, LEGO Plus can operate locally and independently without requiring frequent control from the gateway. In contrast, existing processor-free nodes are essentially based on the direct control of local sensor chips by a remote processor on the gateway. Consequently, the massive raw signals originally exchanged between the processor and chips need to be encoded into a large volume of data and transferred to the air interface, leading to a surge in communication overhead. And next, we evaluate the total power consumption of the node under different communication mechanisms. Initially, when employing Bluetooth communication, we find that the LEGO Plus reduced the power consumption by up to by more than 50% and 91% compared to traditional processor-based nodes and existing processor-free nodes. In contrast, when involving ultra-low power backscatter communication, local control at the nodes predominantly contributes to the power consumption, and hence, when compared with the traditional local processor-based architecture, LEGO Plus reduces the energy consumption by up to 86%. As for the existing processor-free nodes, although they can exhibit some low power advantages in backscatter communication, the substantial volume of data transmission leads to additional power consumption, and consequently, LEGO Plus can also reduce the power consumption by up to 53% compared with these nodes. And finally, we summarize our work. We review that the underlying cause of redundancy and argue that the brute force approach employed by the processor-free architecture, which shifts control to a remote sensor on the gateway with significantly communication overhead, is not that practical. And we summarize all of the task logic of versatile IoT sensing applications into an orchestration of a few automized operations and design a novel hierarchical task description language. And we design a novel hierarchical atomic control circuits to generate a required sensing logic by executing the automized operations with a much simpler architecture than traditional embedded solutions. And we design a lightweight task description framework to efficiently coordinate the control of multiple sensor nodes without requiring a general purpose microprocessor on each node. And thank you for your listening. If you have any questions, feel free to contact the authors by email, and they are waiting for your email and answer your question. Thank you.
Well, let's thank the speaker. Thank you so much. And with this, we conclude MobiSys 2025. In the name of all organizing committee, we'd like to thank all of you for our conference.